This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
In theoretical computer science, we categorize problems by two distinct actions: finding a solution and verifying that a given solution is correct. Problems solvable in deterministic polynomial time belong to the class P. Problems where a solution can be verified in polynomial time, even if finding that solution is difficult, belong to the class NP. Our objective is to determine the formal relationship between these two domains and demonstrate their separation. This separation is achieved not through a specific algorithm, but through a structural analysis of computational containment. We are using a geometric approach. By mapping how these classes include one another, we can test the requirements of the entire system. Mapping this containment allows us to see if an assumption forces a complexity class into a space too small to house its mathematical requirements. Classical methods for separating P from NP have consistently failed to produce a result. These failures stem from two specific structural boundaries, beginning with relativization in 1975. Relativization shows that any proof remaining valid across all hypothetical oracle worlds cannot resolve the P versus NP question. It breaks any argument that relies on oracle symmetry. The second boundary is the natural proofs barrier. This identifies that combinatorial techniques relying on specific cryptographic assumptions or largeness criteria are insufficient to separate these classes. Together, these barriers invalidate many traditional proof strategies by showing they are structurally incapable of distinguishing the two domains. To succeed, a proof must utilize a mechanism that is immune to these specific restrictions. The existence of these walls requires a trajectory that does not relativize, a method that behaves differently in the presence of an oracle. We establish our proof on a strict three-dimensional coordinate plane, creating a fixed geometric arena for our computational classes. First, we define the polynomial hierarchy, or pH. This is a stratification of decision problems defined by alternating quantifiers, where each level builds upon the logic of the one below it. Each ascending layer represents a set of decision problems with increasing complexity. This infinite tower serves as the boundary for all verifiable decision-making in the polynomial model. Next, we introduce a second domain, counting complexity, or hash key. While the hierarchy asks if a valid computation path exists, hash p is the class of functions that count the total number of accepting paths. Verifying a single path is a decision problem. Counting every possible path is an enumeration problem. In this model, counting the paths requires significantly more computational resources than simply confirming the existence of one. This implies a spatial separation between the decision tower and the dense counting core. The connection between these two domains is Toda's theorem. This theorem states that the entire polynomial hierarchy is enclosed within a single deterministic machine that has access to an NP oracle. This shows that the entire infinite tower of decisions is contained within a single counting threshold. The containment is possible because of arithmetization, the process of translating Boolean logic into polynomials. Because arithmetization operates on the internal structure of the circuits, it remains valid even when oracles are introduced. It does not relativize. This makes Toda's theorem a structural bridge that survives the barriers established in Act 1. This containment is a fixed property of the standard model of computation. This fixed relationship provides the coordinate we need to test our initial assumption. To begin the proof by contradiction, we assume that P equals NP. This assumption has immediate consequences for the polynomial hierarchy. If solving is as easy as verifying, the infinite stratification of the hierarchy collapses. Every level loses its distinct internal structure. The entire tower crushes down into a single two-dimensional plane. Mathematically, the hierarchy and P are now the same. We now apply the rules of Toda's theorem to this collapsed state. Because the hierarchy is contained by Toda's boundary, the sphere must compress to encompass this single deterministic plane. This forces a mathematical equivalence. P is now equal to polynomial time with a counting oracle. This equivalence changes how we must view the counting core. If the oracle queries are simulatable in P, then the counting functions themselves must be computable in deterministic time. Assuming P equals NP forces the enumeration of all possible paths into the same deterministic space as verifying a single one. We can now evaluate the stability of this containment. This model requires the deterministic plane to house the mathematical density of the counting core. We have established oracle worlds where counting is strictly more powerful than decision, showing that hash P is not contained in deterministic time. The requirement that counting be simulatable in P contradicts these established oracle separations. The containment fails. This contradiction shows that the model cannot exist as described. The assumption that P equals NP is invalid. The structural relationship between these classes confirms that P is not equal to NP. Deterministic time and verifiable time remain distinct resources. The classes of computation are permanently ordered, separated, and distinct.
This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.